Welcome to part 3 of forces on inclines. In this video, we're going to take a look at how to solve a problem that has to do with forces on inclined planes. And if you haven't watched parts 1 and 2 yet, you probably want to check those out because that's where we set up all the information that we're going to need to solve a problem. So in this problem, we have a block that's at rest on this inclined plane, and because the inclined plane is pretty steep and there wouldn't be enough friction to hold this block up, we have tension over here. So we have a rope that's tied to a rigid support to hold the block up. Let's give ourselves some numbers here. Let's say that the mass of that block is 3 kilograms, and we'll say that the angle of the ramp is, let's go ahead and make that 30 degrees. And what we want to know is what is the tension in that rope that will hold the block up at rest. So we'll go ahead and we'll start by drawing a free body diagram. So we know that we've got the gravitational force, or force weight, mass times g, pulling straight down. We've got a normal force perpendicular to the surface is in contact, and then we've got some tension keeping the object up the ramp. Now, we know that there are two components. We don't typically draw components on a free body diagram. In this example, I'm going to do that just because we're still kind of learning this stuff and we want to remind ourselves how to do this. So we have the parallel component and the perpendicular component of the force weight. Now, if all of this stuff's at rest, then opposite vectors should balance out. So we know that this vector and this vector should be the same, and you can see there I've drawn my tension a little bit too long for this situation, and so the tension over here and over here with the mg parallel should be the same. So in order to solve this problem, what I'm going to do is write out a net force equation, or a force summation, and I'm going to say that the net force in the parallel dimension is equal to the tension minus the mg parallel, and that all should sum up to 0 because the object is not accelerating. And if I'm trying to find tension, that's actually all I'll need because it's only acting in the parallel dimension. So because they both add up to 0, then they should equal each other. Now, from the last video, we saw that the mg parallel component in terms of the angle of the ramp would be equal to mg times the sine of the angle of the ramp. And again, if you don't know where that came from, go check out part 2. So there we would be able to find the tension. So let's plug in some values here. We have 3 times, I'm going to approximate g to be 10, and we're going to put the angle in here for 30. So I have 30 times the sine of 30 degrees, and the sine of 30 degrees is 1/2. So if you put that in your calculator, you should get 1/2. Just make sure you are in degrees, and if you multiply that by 30, you would get 15 newtons. So basically what this is saying is there would be 15 newtons of tension in this rope because the parallel component of gravity that's pulling it down is equal to 15. So to keep those at rest, you would have to have the same. Now let's imagine that we cut this string and the block starts to slide down the ramp. And I'm going to go ahead and say that this ramp is frictionless, since I didn't say that before. And we'll say that if this ramp's frictionless, then while it's sliding down the ramp, we need to draw ourselves a new free body diagram, which is going to have the mg vector pointing straight down, and it's going to have normal force because it's in contact with the ramp. But there's no other forces besides those two because it's frictionless. Now again, I'm going to draw my components on here, even though that's not typical for a free body diagram. You usually don't draw the components, but we'll do that here again. Okay, and so we can see now that in the parallel dimension, which is the one that would be along the surface of the ramp, there's only the parallel component of the force that's acting on the object. There's nothing opposing it. So when I write out my net force summation or equation here, I write net force in the parallel dimension. There is only one force, the mg parallel component, and that is equal to not 0 anymore, but net force, which is m times a. So now when I solve for the acceleration, I see that the m's would cancel out, and I'd just be left with g parallel equals a. Well, I know that mg parallel is mg sine of the angle, and that there would equal m times a. So if the m's canceled out, I'd see that a is just equal to gravitational acceleration times the sine of the angle of the ramp. And that's pretty cool, because you could use this then to find out what the acceleration of something would be as long as it didn't have friction. So that's going to be 10 times the sine of 30 degrees, which is equal to 5 meters per second squared. So I hope that one helps. In a little bit, I will put up some more complex videos of problems that involve inclined planes.